Hello, everyone. My name is Richards, and I'm a PhD student at the Department of Computer Science, ETH Zurich. Today, I'll present our work on debiasing neural networks using differentiable classification parity proxies. This is joint work with Dr. Ece Özkan under the supervision of Professor Julia Vogt. So, in this work, we deal with the problem of debiasing neural networks, and let us first consider the general problem setting. We assume that we have given the features x, which can be described as a p-dimensional real-valued vector. We also observe a protected attribute that is binary valued, and the classification label y, which we try to predict based on the features in x. The protected attribute A usually corresponds to some sort of socially sensitive variable such as race or gender, and ideally we would like to have a classifier that predicts label Y based on features X and whose performance is balanced with respect to the protected attribute A. Of course, we are given a data set consisting of features, labels, and protected attributes that is split into three disjoint parts, in particular, the training, the validation, and the test set. And last but not least, we of course have our biased neural network classifier denoted by f theta that has been trained on the training set without any special consideration of the protected attribute. Our goal is to reduce the bias of the classifier without sacrificing its predictive performance, where mu is the measure for the bias and rho is the performance measure. For example, balanced accuracy. Let us consider one slightly more practical example. In particular, let's say that we develop a neural network-based predictive model based on the data from a hospital that we'll call Clinical Center 1. We train this model based on the training set consisting of features and labels without any knowledge or consideration of the potential biases. Ideally, once we are convinced that the model is good, we would like to deploy it in the external clinical centers, such as Center 2, 3, and 4 here. However, these centers might have local fairness considerations and constraints. For example, for Center 2, we might desire to have a classifier with a balanced performance with respect to the gender. For Center 3, we might care about the ethnicity of our subjects. In Center 4, there might be patients with different insurance types. It is also relatively reasonable to assume that we actually have the access to the model's parameters theta when deploying this model in the Center 2 or Center 3 or Center 4. However, we might not have the full access to the training set from the Center 1 due to, for example, privacy concerns or infrastructure, data sharing infrastructure issues. So it might be much more practical to debias the model based on the local data in those centers, given the local fairness constraints. In this work, as I've already mentioned, we'll focus on achieving group fairness from the perspective of classification parity. We'll work particularly with the neural network classifiers, which have become a model of choice for practitioners, and we will perform debiasing in the so-called intra-processing setting, which basically boils down to debiasing an already trained model by directly adjusting its parameters. The contributions of this work are threefold. We consider differentiable proxy functions for classification disparity that can be optimized efficiently. We propose two simple yet effective debiasing procedures based on pruning and fine-tuning an already trained neural network. And last and not least, we perform comprehensive experiments on tabular benchmarking datasets and fully connected architectures. So let us start out with the preliminaries and some notation. Throughout this paper, we focus on FCNNs and particularly on the multi-layer perceptron architecture denoted by f theta, which takes in input x in RP. And we should remark that the protected attribute may actually be present among the features, or it might be completely exogenous. We do not make any explicit assumptions with respect to this aspect. Of course, this multi-layer perceptron is parameterized by parameters theta, which is just a set of weight matrices, and we assume that it consists of capital L intermediate layers. We also use HL of X to denote the activation layer vector for layer L of this MLP. And last but not least, the final classification based on this MLP is given by a thresholded sigmoid output, where the threshold T between 0 and 1 has been tuned on held out validation data. And here is one example of the architecture that fits this description. In particular, this is the architecture we use in our experiments, consisting of 10 intermediate layers with ReLU activations, dropout and batch normalization modules. So in order to be on the same level, let us recap what is classification disparity. According to the classification parity, we say that a classifier is fair if some derivative of its confusion matrix, for example, true positive rate, is even across the groups of the protected attribute A. There are various metrics for classification parity, but arguably the two most popular choices are statistical parity and equal opportunity difference, where the SPD is given by the difference in the conditional probability of positive prediction given the value of the protected attribute, and the EOD is given by the difference of the true positive rates across the groups of the protected attribute A. Then in this paradigm of classification disparity, debiasing is just a procedure of mitigating classification disparities measured using the metrics such as above. In this paper, we focus on the SPD and the EOD, although the methods are extendable to the other metrics of interest. So what debiasing algorithms are there? There is actually a whole zoo of debiasing methods, and one practical taxonomy puts them in the context of machine learning model lifecycle. In particular, we have pre-processing, in-processing, and post-processing algorithms. Pre-processing usually focuses on reweighing, resampling, or transforming the data itself. For the in-processing, we incorporate our bias considerations and constraints directly into the loss function or into the training process of the model. And last but not least, the post-processing techniques usually adjust the model's predictions post hoc, and importantly, they treat the model as a complete black box. In this paper, we focus on the relatively new class of debiasing approaches, the interprocessing. These, similar to the post-processing, work post hoc. However, instead of adjusting the predictions, they directly adjust the model's parameters. And importantly, the interprocessing techniques don't treat the model as a black box and don't require the knowledge of the protected attribute at test time. This is an important difference and arguably makes interprocessing slightly more practical in certain applications. So in this work, in order to be able to reduce the bias efficiently within the neural networks, we utilize differentiable parity proxies. And in particular, we work with the SPD and EOD and propose the following proxy functions given in this slide. As you can see, the SPD function requires the knowledge of the output of the neural network and the protected attribute, whereas to compute the EOD, we also additionally need the ground truth classification label. The intuition is to optimize these bias proxies directly and efficiently, and to design interprocessing algorithms that would optimize them. But one might ask, what is the relationship between these parity proxies and the actual criteria such as SPD and EOD, and why is it even sensible to optimize these proxies? Well, similar to the previous work, which has mostly focused on the fair linear classification, and particularly on the logistic regression and SVM models, we have demonstrated that these proxies correspond to the empirical estimators of the covariance between the protected attribute and the decision boundary. In case of the EOD, this is the covariance conditional on the positive ground truth label. So, how do we optimize these proxies? Well, often debiasing can be viewed as an instance of constraint optimization. In particularly, most of the work out there focuses either on optimizing the performance subject to the bias constraints or minimizing the bias subject to the performance constraints. So basically, in our work, we adopt an approach similar to the highly related work on interprocessing methods. In particular, given a performance measure rho, a bias measure mu, and a bound on the bias epsilon greater than 0, we try to maximize a bias constrained objective phi that is given by this expression here. Essentially, the bias constrained objective is equal to the performance if the absolute value of the bias is below epsilon, and it's equal to 0 otherwise. So as I already mentioned, we try to maximize this phi for both of the techniques that we'll introduce in the next slides. So one of the methods that we explore in our paper is pruning. Pruning refers to the removal of the parameters within the neural network model, and most of the pruning literature out there has concentrated on pruning as a means to reduce memory complexity, improve computational efficiency, and so on and so forth. But in this work, we focus on pruning to achieve a debiased model. The intonation is basically to remove individual units or neurons from the neural network, in particular those units that contribute to the bias the most. But how can we measure units' contributions to the bias? Well, there is a lot of literature out there for interpretability and explainability focusing on attributing importance to individual neurons. And in particular, inspired by some lines of work in the previous literature, we propose the following gradient-based statistic to measure the influence of a single unit with respect to the bias. This statistic for unit J in layer L essentially boils down to taking the partial derivative of the differentiable bias proxy with respect to the activation within that unit. This partial derivative has to be averaged across the data set. It can also be averaged across the mini batch if the memory complexity is the constraint. Using this statistic, we can then decide which units to prune within the network. And here's the outline of the procedure for the pruning algorithm. We start out with our biased classifier f theta, and then for every layer L, for every unit in that layer, we evaluate the influence of the unit with respect to the bias. Eventually, based on this influence statistic, we decide which units to prune. In this case, for the sake of example, we prune units one by one. Then after removing this unit, which essentially amounts to setting certain weights in the weight matrices to 0, we evaluate the performance, the bias, and the bias constrained objective of this pruned network f theta tilde on the held out data. And then we continue pruning until the maximum level of sparsity is reached. And at the end of the algorithm, we return a pruned network that maximizes the bias constrained objective. And this is our debiased network. We'll see from the empirical results that this algorithm is very effective in practice and only few pruning steps are necessary. Another algorithm that we consider is the bias gradient descent ascent, and it's quite similar in that it also tries to directly minimize these or maximize these classification parity proxies that we have introduced. An important note is that they are differentiable, so in principle we can directly minimize or maximize them by gradient descent or ascent depending on their sign. And the procedure then again is very simple. We just have to fine-tune our biased classifier f theta in order to adjust its weights. Essentially, this boils down to fine-tuning for just few epochs with a small learning rate compared to the initial training time of the classifier. In practice, we implement bias gradient descent ascent as the mini batch gradient descent. However, other optimization procedures can be used alongside with the Adam optimizer. And in the end, we again return the fine-tuned network f theta tilde such that it maximizes this bias constrained objective on the held out validation data. So in order to test our algorithms that we have proposed and compare them to some other baseline techniques which focus on post-processing, we have performed a range of experiments mostly focusing on tabular data and fully connected neural network architectures. In particular, we have had a look at the range of debiasing methods, including our own, and we focused on simple tabular benchmarks such as adult, bank, and compass data. In addition, we have considered a clinical mimic3 data set. We have considered a variety of protected attributes shown in this table here. So let us first have a look at the qualitative results. In this slide here, we can see the changes in the balanced accuracy and the statistical parity difference throughout the process of pruning and bias gradient descent ascent achieved on the compass data set. We can see that for both bias and pruning and bias GDA, the bias goes down throughout the process of the algorithm and is effectively driven towards zero at a certain point. But we also can see that the balanced accuracy throughout both algorithms does not decrease considerably. We can see that for the bias GDA, the decrease is particularly non-existent. In general, the results look assuring and kind of demonstrate that we can reduce the bias considerably without hurting the balanced accuracy of the neural network. However, if we look at the adult dataset, the results look slightly less optimistic. We can see that while in certain cases the bias is reduced, there is also a considerable decrease in accuracy for pruning, and there is also a considerable variance. In certain runs, the algorithm fails to debias the classifier. For the bias GDA, the situation is slightly better. However, there is still a considerable reduction in the balanced accuracy after debiasing and considerable variance across the runs. Looking at the quantitative results here in this table, we can see median bias constrained objectives for the upper bound of epsilon equal to 0.05 across 20 train validation test splits. We have performed debiasing with respect to the both bias measures, the SPD and the EOD, for all of the data sets. Looking at the Bank, Compass, and Mimic3 data sets, we can see that in all of the cases, pruning and bias GDA on average achieve the best performance and offer the most balanced performance across all of these data sets and bias measures. However, looking at the adult data set, we can see that here bias GDA and pruning seem to successfully debias, but at the same time hurt the performance considerably, performing worse than reject option classification, particularly for the SPD metric. As already explained, we have seen that there is a big variance with respect to the runs, and one of the reasons could be that generally interprocessing techniques are sensitive with respect to the initial conditions and the initial bias of the classifier. Overall, the experimental results look encouraging and suggest that our techniques are viable, particularly when compared to the post-processing approaches. We have also performed additional experiments on the synthetic data in order to see how pruning and GDA perform under varying initial conditions on nonlinear data. Here you can see the results for both of the algorithms. The x-axis here shows the changes of theta, which is the parameter regulating the degree of bias within the data set. In particular, in orange, we can see changes in the bias in the statistical parity difference of the original neural network classifier. And as theta decreases, this bias goes up considerably from 0 to 0.5. At the same time, throughout the changes of theta, the accuracy of the original classifier doesn't change at all. In the blue, we can see the bias constrained objective attained by both pruning and bias GDA. And as you can see, for low degree of bias, both algorithms successfully reduce the bias while not hurting balanced accuracy at all. Whereas when the bias is relatively high, when the statistical parity difference is above 0.2, both algorithms result in a significant reduction of the balanced accuracy, which suggests that when the initial bias is high, it might be prudent to resort to other debiasing procedures, for example, in processing or post-processing, in order not to hurt the accuracy as much. So in summary, in this work, we have considered the problem of debiasing neural networks in the intra-processing scenario. We have studied differentiable proxy functions for the SPD and EOD that are related to the covariance between the decision boundary and the protected attribute. And we have proposed two simple yet effective intra-processing algorithms that utilize these proxies based on fine-tuning and pruning. Our first experimental results focusing on tabular data and fully connected neural networks look very encouraging and suggest that our methods are viable, particularly when compared to post-processing methods. If you're interested, please check out our paper for more details, and thank you for your attention.